All right.
I do have a question, but not about the previous lecture.
Okay.
So my background is in theoretical computer science, and it's been a while I'm looking for a good resource to read about quantum. So I've tried a couple of videos and books, but sometimes they're really from like a physics point of view. So I wanted to know if you have any suggestion about that.
Yeah, I do. I've been looking at a number of different books. The one I like best is Quantum Computing for Computer Scientists. And it's written by a guy who's at like City College. I've actually emailed him with some questions and he sent me an errata list, so that's kind of nice. I also recommend IBM's online text. It's called Qiskit, Qiskit. We're going to be looking at some of that stuff later on. Um, there's a lot of math and there's some physics, but you know, you can get through it. But those are the ones I'd recommend. All right.
Thank you.
Any other questions from last time? If not, let me get started. Okay, so I'm going to TD share. Let's see. Gonna share. There we go. That one. All right. There we go. I assume everybody can see that. So let's talk about some of the key points of last time before we get into some of the new stuff. So we saw the kind of 30,000-foot picture of a quantum computer. I described it as the world's most expensive coprocessor, controlled by a classical machine, sets up some initial quantum state, and then causes the machine to evolve that state into a final state, which is then observed. And the classical machine cannot actually read anything about the quantum state except at that final observation level. And we'll be talking a little bit more about that. So we looked at the state of a single qubit. And in the lower right-hand corner there, you see that two vector that's based on those two angles, theta and phi. That's kind of the most general form of the state of a single qubit. It is a superposition of kind of the 0 and 1 basis states, the superposition, the magnitude of that superposition being determined by the sine and cosine of that angle theta. And there's also a phase difference between the 0 and 1 state determined by the angle phi that you can see there. So if we remember how we derive that by imposing the two constraints, that it's a unit vector and that we can ignore global phase. And then we noted that if we've got two angles, that maps nicely to the surface of a sphere. This is called the Bloch Sphere. And we've got the 0 state at the North Pole and the 1 state at the South Pole. We're going to see the Bloch Sphere one more time today, and then after that, not at all. You know, don't get overly worried about whether you quite understand this, but there it is. And we looked at the how two independent qubits combine to produce a 2-qubit system using this thing called the tensor product, which is very simple, basically the product of all possible combinations of those two-element vector states. And then we noted that there are plenty of quantum states that cannot be represented by the tensor product of independent qubits, and those are the entangled states. And we looked at one entangled state. This is called the Bell state. And this particular simple state cannot be represented by a combination of two independent qubits. They are not, these two bits are not independent, they are entangled. And that means that their probabilities of being measured are highly correlated with each other. And this is kind of the thing that really annoyed Albert Einstein and his friends, because if these two qubits were separated in space by, light years, their behavior would still be correlated. And that's a whole interesting topic, but a little bit beyond both today and my own personal understanding of quantum mechanics. We reviewed the gate model quantum computer, that this is all about. The idea that we are going to take that initial state vector and simply rotate it. Everything that we can do to a state vector is a rotation or a reflection. So we're going to rotate that vector to one with a very high probability of observing the result that we want. But instead of rotating it as one big step, we're going to rotate it in small steps so that those steps can be understood and can be implemented in actual hardware. Those steps are called gates. And a quantum computer, is called universal if it implements a set of gates, in other words, a set of small rotations that can achieve any possible rotation. And you can think of this as quantum machine language. So that's kind of the summary of where we were. Let's see. Yeah, we looked at the simplest logical NOT gate. It's a 1 qubit rotation. And what it does, it simply flips basis state 0 to state 1, flips state 1 to state 0. You can think of this as the little truth table of the whole thing. And in the general case, it flips the two components of the quantum state. This is a possible rotation. You may remember that rotations are described by unitary matrices, where their conjugate transpose is their inverse. And this is an example of a real simple unitary matrix. So I think that's where we were. Yeah, and we also looked at the idea that any Boolean function of n variables can be computed, can be understood as a unitary operation, as a simple rotation, if the circuit is in this form, where you've got the n inputs, those are the x's, and then you've got a special y input, and the output is the exclusive OR of y and f of x. And of course, if I make y 0, I just get the function that I want. So this is how you can make any Boolean function. I'm not going to prove that this is always realizable, but it is. All right. We looked at I think we finished with an example of a logical OR that's kind of in this form. And it ends up having 3 qubits of input and 3 of output. So it's an 8 by 8 matrix. And it just, in effect, exchanges certain elements of the 8-dimensional state vector. And the reason it exchanges those is because of the exclusive OR. That's what kind of that exclusive OR is doing. And this is the kind of thing that you can do. All right. Any questions on the review? All right. Let's look at some interesting stuff here. So there are a number of single qubit gates that are used often enough, and those are known as the X, Y, and Z gates. We've already seen the X gate. That's kind of the NOT gate. But there are 2 others, the Y and Z gates, and these are called the Pauli gates after Wolfgang Pauli, the physicist who used them for other purposes than quantum. He introduced them, and I'm not entirely familiar with what Pauli did with them, although I think you can combine them to achieve any rotation you want if you do it the right way. But in any event, these are gates that are often used in quantum computing. We're going to use the X gate a lot. I mean, that's just a simple NOT, if you will, NOT gate. We're going to use the Z gate some. I am showing you the Y gate. We're not actually going to use it, but I'm putting it up there because everybody who talks about quantum computing has to mention these 3 gates, the Pauli single qubit gates. And if you want to see what they do, first of all, they have symbols. When you draw a diagram of a quantum computer, we use the following symbols for these gates. And when I say we use them, what I mean is that IBM's circuit composer uses them. I don't know quite how standard they are, but I've basically used the same symbols that we're going to see later when we look at some of the IBM stuff, because those are quantum computers that ordinary people have access to. If we go back and take one more look at the Bloch sphere like this, all right, take one more look at that. What you'll notice about this is that the North Pole, the three axes of the Bloch sphere correspond to certain unit vectors, like the North Pole, that z-axis is the kind of zero basis state, and you can see that up here. And the x-axis, being on the equator, is a superposition, equal superposition of 0 and 1, just like this. All right, that's an equal superposition of 0 and 1. That's the x-axis of the Bloch sphere. And then finally, the y-axis is also an equal superposition of magnitude, okay? But there's a phase difference. There's a 90-degree or pi over 2 phase difference that looks like this. Okay, and if you multiply these unit vectors, x, y, and z vectors that kind of point along these axes, by the x, y, and z gates, you'll notice, for example, that the x gate times the x unit vector equals itself. And the same is true of the y gate, and the same is true of the z gate. All right, you can say that these unit vectors are eigenvectors of those matrices. And the reason I bring this up is because we know that these matrices are rotations. And the question is, what rotation? And if you have a rotation of a vector that produces the exact same vector, the only possible thing it can be is a rotation about that vector. Right? That's the only way of rotating a vector that doesn't change the vector, is if the vector is the axis of rotation. So what this means then is that these x, y, and z gates are simply rotations about the x, y, and z axis of the Bloch sphere, and indeed they are rotations by pi over 290, pi 180 degrees in the Bloch sphere itself. Again, don't worry too much about whether you're going to remember that, but I just want to give you a sense of how you figure out what these things are rotating in this simple case. All right, so those are the single qubit gates. We're going to be looking a lot at the x gate, and we'll use the z gate a little bit. All right. One more thing about the Pauli gates, and the question is, what do they do to a quantum state, to the general 2-bit or 1-qubit quantum state? And what you can see is that if I take that general state and multiply it by these things, that what happens is the x and y gates essentially flip the amplitudes of the 0 and 1 state, and then they all apply some sort of phase shift. And you can kind of work this out. You have to remember to deal with the global phase correctly, because our convention is that the relative phase is always expressed in this second component here. That's an arbitrary but consistent convention that everybody follows. And if you factor the phase out so that that's the case, that you can work these out. So that's basically a good description of these single qubit gates that we're going to see. Now, one other very important gate that we're going to see a lot of, which is also a single qubit gate, is called the Hadamard Gate, and it looks like this. All right. This is also a unitary matrix. You can confirm that. You can take the complex conjugate, which in this case is itself, and discover that it's its own inverse. And what the nice thing about what this gate does is it takes the zero state here, all right, it takes the zero state and turns it into an equal superposition of 0 and 1. And so whenever you need to create an equal superposition of 0 and 1, you can start off with the 0 basis vector and apply the Hadamard gate. And there's a shortcut symbol for this equal superposition, and that's it right there. And so in kind of the simplified form, I can kind of write it like this. If I need an equal superposition, I start with a 0 state, and I apply the Hadamard gate. Similarly, if I start with the 1 basis state, what I get is also an equal superposition of amplitude, but a phase difference of pi. Because, you know, -1 is the same thing as a pi radian phase difference. And that's the shortcut symbol for this state, the state of equal amplitudes, but phase difference of pi, and we can write that like this. So that's the Hadamard gate, and we're going to use that a lot when we need to create an equal superposition. Any questions so far on this stuff? All right. Let's see here. Move my... Okay. Another extremely important gate that we're going to look at is called the controlled NOT gate. It's kind of like a NOT gate, but there's a control qubit. So you can see the symbol here for a NOT gate. Okay. And the idea here is that if the control input is logical 0, in other words, the 0 basis state, then nothing happens. Because 0 exclusive OR y is just y. So nothing happens. But if the control qubit x is in the 1 state, then the y state is flipped, kind of like a NOT gate, because that's what exclusive OR does. And if the 2 input qubits are in a superposition of states, the output is going to be in an interesting superposition that we're going to get into. But this is what the matrix looks like. It is a unitary matrix, and what it does, since I've got 2 qubits, of course, I've got a 4-dimensional complex vector state, and all it does is swaps those ones in red, just swaps those 2 components. All right, that's what the XOR function does. That's what it does. All right, so that's a very important, we're going to be using this a lot, because now we begin to see how we can put together some logical operations. We've got a controlled NOT gate. Another extremely, but before we get into the next one, so earlier we talked about this Bell state, this state of 2 qubits that's entangled. So let's see how we can use a Hadamard gate and a controlled NOT gate to generate this interesting entangled Bell state. Okay, so the way it works is we're going to start off with the inputs in the 0 state. The computation is going to flow from left to right. The Hadamard gate turns that 0 state into the equal superposition state. Okay, so now we've got these 2 independent, unentangled qubits. Let's put them together using the tensor product. Looks like that. All right, so there's a very simple tensor product. And that is the state that we get. This is, again, an unentangled state because it can be generated by this tensor product. The shortcut for it is right here, namely that the tensor product of the 0 state and the plus state is now written as this 0 plus thing. Okay, so that's the input to now my controlled NOT. What does controlled NOT do with it? Well, controlled NOT takes that vector and multiplies it by the control NOT matrix to yield this. And that is the Bell state. That is an entangled state. It cannot be represented as 2 independent qubits. And so the control NOT is often called an entangling gate. All right, it takes unentangled inputs and it can produce an entangled output. And it can do that if you proceed it by this Hadamard gate. All right, so that's just a really simple example of a quantum circuit that can produce, in this case, our Bell state. All right. Now, there's another very important gate that is very much like the controlled NOT gate, except instead of having one control input, it has two control inputs. And the output is the exclusive OR of the input and the logical AND of the two control bits. So you can see the logical AND there. Okay, so that's what this is kind of like an AND gate, right? If you want to make an AND gate in a quantum computer, you use this. It's called a Toffoli Gate, after the guy who invented it, who was in that photograph that I showed on the first slide of the very first day, Tommaso Toffoli, colleague of Ed Fredkin. And he came up with this idea. And all the Toffoli Gate does, which is what that exclusive OR gate does, is it swaps these two elements of the state vector. Right? That's what a Toffoli Gate does. And we'll be using some of those in a minute. So I talked about a universal quantum computer and a universal gate set. This is an example of a universal gate set. All right, there's the controlled NOT, which is sometimes called CX. There's the NOT gate and two other gates that I'm going to briefly mention, although you don't have to worry about whether you quite understand how they work. One of them is called the square root of X gate. And the reason it's called the square root of X gate is if you multiply it by itself, you get the X gate. It's kind of interesting, all right, that you can have kind of a square root of X gate, but you can, and it's called that because if you multiply it by, if you square it, multiply it by itself, you get the X gate. And then there's this RZ gate here, all right, which is a parameterized gate. It takes a parameter phi and it applies a phase to one of the components of the gate. So that's what this thing does. The reason I'm showing you these is because these are exactly the gates that the IBM quantum computers that we're going to be seeing later use. They only implement these gates, nothing else, just these four. And from these four, because this is a universal gate set, you can make anything, any rotation in the quantum vector space that you want. I'm not going to prove that that's the case, but that's an example of a very simple universal gate set. I can make anything I want from these, or at least IBM can. And doing that, by the way, is what a quantum compiler does. You give the quantum compiler an input using all sorts of fanciful gates that the hardware cannot implement directly, but then the compiler turns that into combinations of the gates that the machine actually implements. And that's how that works. We're gonna be seeing some of that later on when we get into some of those details. All right. From these universal gates, I can make a Y gate. All right, so that's how I make a Y gate. And you can work these details out if you want. I'm not going to, but as an exercise, if you feel like it, I mean, I've promised there won't be any homework, so you don't have to. But if you want, you can work those details out. I can make a Z gate by simply using the RZ with a parameter of pi. I can make a Hadamard gate like this. All right, it's not obvious why that works, but you can work out the details if you feel like it. And see that it does indeed create a Hadamard gate. Here's an interesting thing. I can use 3 controlled NOT gates to swap 2 qubits. You know, put 2 qubits in on the left, and on the right, they come out swapped. Which is, by the way, the exact same thing as the classical 3 exclusive OR swap. I don't know how many people are familiar with this bit hack. You know, probably from the 1960s. But if you want to swap 2 numbers without an intermediate temporary, you can do that with 3 consecutive exclusive ORs. And you can do that, the same thing in a quantum computer using 3 of these controlled NOT gates. So that's what an example universal gate set looks like. Now we're going to get into some really interesting, and by that I mean weird stuff. All right. Phase kickback is going to be an extremely important part of the Grover algorithm and many different quantum algorithms. It is a weird property that has to do with interference because I've got these phase shifted quantum states. So we've got a little circuit here with a NOT gate, two Hadamard gates, and a controlled NOT gate. I'm going to start the computation on the left with the 2 qubits in the 0 state. All right. Next, that NOT gate turns the 0 into a 1, as NOT gates are wont to do. The Hadamard gates, they turn the top one into the plus state, basically that equal superposition state, and they turn the bottom one into the equal superposition but phase shifted, that minus state. And now we're about to send them to, these are now still independent, not entangled. Let's figure out what these things look like using our tensor product. All right, since they're independent, we can do that little tensor product thing, and here's what we get. We get something that can be written shorthand as the minus plus state. All right, where Q0 is always the least significant bit, Q1 is a more significant bit, and I write the minus state, I write it minus plus rather than plus minus because I write it most significant to least significant from left to right, the way a computer scientist would. Not all textbooks write it that way. You just have to be consistent about it. I think physicists tend to do it a different way, but in any event, it's the way we're doing it. So what happens when you take this state, all right, this state here, which is still unentangled, and pop it through my entangling controlled knot? Well, we know what happens. Those things that I marked in red get flipped, right? That's what the controlled knot does. Now, let's look at this state. Is this an entangled state or an unentangled independent state? Well, can I write it as a tensor product? And the answer is I can. I can. It is this tensor product. I can write it that way. So the output is not entangled. Now, this is the tensor product of what two states? Well, it's the tensor product of a minus state with another minus state. In other words, it looks like this. All right. And because these are now independent, what that means is that the top qubit is in the minus state, and the bottom qubit, and the bottom qubit is in the minus state. Okay, because I now have these two independent qubits, both of them in the minus state. So here's the weird thing that just happened. Okay, I've got a controlled NOT gate where this is the control, and this is the thing being controlled, and yet the thing being controlled doesn't change. It's the same. The state is unchanged. And the thing that is supposed to be the control is the one that's actually changed. And this is called phase kickback. Because the bottom qubit is out of phase, that phase difference is kicked back to the control line. And when I first saw this, I really struggled to understand it. But the math is the math. It's real simple. All right, the math is the math. These are the rules. And so when you have a circuit like this, right, this phase shift here gets kicked back to the other control line. And this is going to become, this is a really important operation that we're going to see in Grover's algorithm and in lots of quantum algorithms. All right, questions on this? Because this, again, this was a little confusing to me when I first saw it. How's everybody doing with this concept here? Everybody seems to be happy. All right, as I said, the math is the math, right? Okay, so let's do the same thing with the Toffoli gate. All right, the controlled NOT gate with two control lines. All right, so just like before, I started off with all the qubits in state 0. right? This NOT gate gives me a state 1, and the Hadamard gates give me my equal superpositions, with the bottom one being out of phase, right? That goes into the controlled NOT gate, and my two control lines are the equal superpositions. So what happens now? All right, so these three independent qubits combine with this tensor product here, and that looks like this. All right, so that's what this state looks like. Remember these basis vectors? Remember, we've got 3 qubits, so that's an 8-element or 8-dimensional quantum state, and these are the basis vectors that you get when you do this tensor product. It's simply the 0, 0, 0, or basically 0, 1, 2, and 3 components, again, saying in binary, are positive, and components 4, 5, 6, and 7 are negative. The square root of 8 is just a normalization factor to make this a unit vector. That's what this is. That's what goes into the controlled NOT gate. All right. And what comes out of the controlled NOT gate, as we remember, what controlled NOT does is it exchanges those two components, the ones that I marked in red. So what does that look like? All right. What does that look like? Well, here's what it looks like. This state here is the tensor product of the minus state and this state here. So the minus is, and that's the most significant, that's Q2. That's what's coming out of the control. That's what's coming out right here. That's independent, but the other 2 qubits are now entangled, because this state, these 2 qubits here, that's an entangled state. And so what happens if you look at this, all right, is that the minus state came in and is unchanged, just passes right through, but the top 2 qubits are now entangled, and here's the phase kickback right here. What has happened is that one of the 4 components of that state, one of them has been selected, and the sign has been flipped. Or another way of looking at it, there's a 180-degree relative phase of that one component. And so what this does is the AND function of the Toffoli gate selects the AND state, in other words, they're both 1, and flips it, changes the phase. And that's what it does. That's going to be really important. All right. And in fact, we can generalize. So before I get even further down this crazy path, any questions about this? All right. Everybody seems happy, or at least maybe hopelessly confused, but okay. All right. So again, the math is the math, right? That's what it does. So this is what a quantum oracle is, and these come up a lot. This is a generalization of what we just saw. So imagine that I've got some quantum state with an arbitrary number of qubits. And one of the components, so let's say I've got 10 qubits, right? So I've got a 1024 element complex vector. And I want to mark one of those elements, one of those 1024 elements, by flipping its phase, by making it essentially negative, if you will. And so that one component I'm going to call W for the winner state. That's the winner. That's what you're trying to find. And so all of the states that are not the winner state are left alone, and that winner state has its phase flipped. So this is what a quantum oracle is. It is some sort of black box, some sort of magic logical function. And remember, we can make any Boolean function we want out of gates that is capable of deciding which of those, maybe 1024, maybe 4 billion, however many is capable of deciding which is the one that you're interested in, and marking it by flipping its phase. And the circuit is very simple, just like we saw before, right? We start off with a 0 state here, turn it into a 1, use the Hadamard gate. And what this is essentially that This is that circuit that we said we could always make, some function of inputs that produces the exclusive OR, because that's what this controlled NOT gate is going to do. And as we saw with phase kickback, this is a phase kickback circuit. That minus state gets passed through undisturbed, and the output here is a highly entangled state where one of the components has had its phase shifted. And these kind of circuits are used all of the time, all of the time. When you've got a whole bunch of states and you want to have some way of picking one, you design some logic in here, some black box logic in here that controls this NOT gate down here, that turns the NOT gate on whenever the logic is satisfied. And because of the phase kickback property that we saw before, it marks that winning state. Right, so that's the generalization. That's that quantum oracle thing. You can also arrange this, by the way, so that there's more than one winner. We're only going to be looking at the one winner state, but you can generalize this if you want to an arbitrary number of winners, but we're not going to do that. Just trying to keep it simple. All right, so that's the quantum oracle. So, having set the stage, let's start looking at Grover's search algorithm. So imagine we have an unordered list of n elements. There's no particular order or structure to it. And we're looking for one of them. And it's going to be a quantum oracle that decides which one. Right? We don't know what's in there. Somehow, somebody has given us an oracle that picks out the one that we're trying to find, but we don't know which one it is because it's a black box. And the question is, how many times do you have to query the oracle to find the winning state? And on a classical computer, you'd have to query the oracle about order n times. I mean, on average, n over 2 times. Worst case, n times. You have to ask it every time. Grover's algorithm, we're going to query the oracle in order square root of n times. All right. So, for example, if we had, 1,000,000 elements, right? So that would be a million elements is what, a 20-qubit state vector. It would take, approximately a million tries on a classical computer. We're only going to have to query the oracle about 1,000 times instead of 1,000,000 to find that winning state. That's Grover's algorithm. So how does this work? All right, it's kind of a remarkable conclusion. So it works by a process that's called amplitude amplification, which is, again, something that's commonly used in a quantum computer. So let's say that we start with an initial quantum state where everything, all of the components are in equal superposition. So maybe we've got 1,010 qubits, 1,024 elements, and the amplitude of each element is the same. That's the amplitude, and they're all the same. All right, we can use Hadamard gates to create this equal superposition. And one of these basis states, one of them is the winner. We just don't know which one it is. We don't know which one it is, but one of them is. The quantum oracle knows which one, but we don't. The first thing that the algorithm is going to do is use phase kickback with the quantum oracle to do this, all right? To select or to mark that winning state by adding 180 degrees or pi radians worth of phase, which, again, phase of pi radians by Euler's formula is the same thing as a negative amplitude. All right, so now the picture looks like this. That's what the oracle has done for us. It's marked this winner. All right, but the amplitudes are still have the same magnitude. Now, let's imagine that we can compute the average amplitude of all of the basis states. That average is going to be slightly below the amplitude of most of them, because that negative amplitude of the winner state pulls the average down just a little bit. All right, so it'll be slightly below. Let's imagine again that we can compute that average amplitude. In a minute, I'm going to tell you how. Now, the next step is we're going to reflect all of these amplitudes about the average. Okay, so for example, any amplitude that's above the average will now go down to the same amount below, and anything that's below the average is going to go to the same amount above, okay, because we're just going to be reflecting about that average, and it's going to look like this. So now, all the non-winning basis states, instead of being slightly above average, they're now slightly below average, and that negative one has been flipped a lot, by approximately 3 times its amplitude, right? Because it is approximately 2 amplitudes below the average, and the average is about 1 amplitude above 0. And when you flip it, it has now been amplified by about a factor of 3. All right, so it's now beginning to stand out. It's now beginning to stand out. Now, if we repeat this about approximately the square root of n times, this use the oracle to make the amplitude negative and then reflect about the average. If we do that about the square root of n times, we're going to see that we end up with a vector where the amplitude of the winner is very close to 1.0, and the amplitude of everything else is very close to 0, extremely close. So let's see how that works and how many steps it takes. All right. So first of all, let's understand what this average is. That is an average, that is a matrix that is simply capable. You give it a vector, you give it a column vector, multiply it by that vector, and the output is going to be a vector where every element is simply the average of all of the amplitudes of the input. All right, that's an averaging matrix. This is not a rotation, though. This is not a unitary matrix. It's not a rotation. But that's not exactly what we were doing. That's a piece of what we were doing. But here's what we were doing. Remember what I said, that when we reflect about the average, okay, the amount by which a vector is above the average now becomes the amount by which it's below the average. That's what that minus sign is doing here. So this is what we're actually doing. We're actually taking my vector, averaging it, and subtracting from that the vector minus the average. So again, however much it was below the average, that's, however much it was above the average, that's how much below the average it's going to be. That's what we're actually doing. All right, and that looks like, all right, I can rewrite that like this, right? I can just rewrite, that's a simple rewriting of what I just wrote. So I'm now multiplying my vector by twice the averaging vector minus the identity matrix. And this 2a minus I, that is a unitary matrix. That can be done in a quantum computer. And let me prove that, because it's a simple proof. I promise there will never be any proofs that won't fit on one slide. Okay, so to prove that this is unitary, I have to prove that its conjugate transpose is its inverse, right? So there's the conjugate transpose, and I need to prove that when I multiply that by itself, I get the identity matrix. Conjugate transpose works just like a normal, transpose with real elements. You can bring that inside, basically distribute it over the elements inside. And then the conjugate transpose of the averaging matrix is itself, right? If I transpose it and take the complex conjugate of 1, I get the same matrix. And the same thing is true of the identity matrix. The identity matrix is its conjugate transpose. So if I now multiply this out, I get this, all right? Those are my matrices. Now, it's pretty clear that A times A is just A, because if I average something and then average it again, well, nothing's going to change, right? I can average it as many times as I want. It's still going to get the same thing, right? So what I really have here, and by the way, of course, the averaging matrix times the identity matrix is clearly just the averaging matrix. So I've got that, which reduces to the identity matrix. Therefore, This is unitary, and this can be done on a quantum computer. So this amplitude amplification, we've now demonstrated that somehow it is a rotation, all right? I mean, I don't quite understand what the rotation is. We're going to have to come up with some gates that can implement this, all right? But that's the proof that what we're doing here, that diagram that I showed you, can be done on a quantum computer. All right, so how are we doing so far? I see some people are shaking their heads like, yeah, maybe they quite get it, okay? All right?
I have a question.
Yeah.
The use of the oracle, because I guess I'm used to oracles in cryptography where the oracle is sort of like a theoretical thing, but it seems like you're saying that the oracle here actually kind of exists. Like you can actually come up with a Mark winner oracle.
Correct.
And then you use that to run this algorithm.
Yes, correct. This is not, the quantum computing community uses the word oracle, but it is nothing like the complexity theory oracle, which I just learned actually from Steve earlier today. I'd never heard of it, but it's a thing, but that's not this thing. And indeed, you already saw one. The one that I made with the Toffoli Gate that picks that one winning state, you can make these. In fact, later on, we are going to make one out of Python code and run it. Okay, so yes, you can really make these.
Okay, great. Thanks. That's awesome.
Yep. Okay. So let's look a little bit more at amplitude amplification. So imagine that I'm going to define x sub k to be the amplitude of these n-1 non-winning components after k iterations of Grover's algorithm, and y of k to be the amplitude of the one winning component after k iterations of Grover's algorithm. And I'm going to use this then. So what the oracle then does, all right, is that state k here, it's basically just the sum of all of these basis states that are not the winner. And then the oracle negates the amplitude of that winning state, right? So that's kind of a shorthand way of saying what the oracle does. Don't worry too much about that. So the average of all of these amplitudes is simply n-1 times the x's minus the y divided by the total number. That's the average, all right? I've got n-1 x's. I've got one y that's been negated by the oracle, divide by the total number, that's the average. So what does this look like? Okay, so in the next iteration after k, in other words, k plus 1, remember it's twice the average minus the identity. So there it is, twice the average minus the identity. And this can be rearranged algebraically to look like that. All right, so that's a recurrence relation, if you will, for the amplitude of the non-winning states as Grover runs. And you can do the same thing on the y side. Okay, again, we have twice the average. It's the same average, but instead of minus x, it's plus y because the y's been negated. And again, I rearrange it like this. And I rearrange it this way because this term is the same as this term. The only difference are the other terms. So, having done this simple algebra, I said, okay, let me plug these formulas into an Excel spreadsheet. Right? This is what I actually did when I first came up with these derivations, which are pretty simple. I said, okay, I'm going to plug this into an Excel spreadsheet and see what happens. So here it is. I've got, in this case, 8 qubits, right? So I've got 256 states, 256 components of the quantum state. And this is that common term here. And this is what happens to the x and y components as I iterate Grover. And in the final column is the probability that I'm going to measure the correct answer being the winning state. So first thing I noticed is that indeed the y amplitude is very close to tripled after the first iteration. We kind of expected that geometrically. that the y component after one iteration would be approximately 3 times what it was before. So you can see that right here. So I was happy about that. So then, okay, so I've got 256 elements. The square root of 256 is 16. So I'm thinking, okay, after 16 iterations, I ought to be doing pretty good. But what I discovered is, well, I'm doing okay, but the best, the best answer is after 12 iterations, not 16. That's over here. Right? After 12 iterations, the probability that I'm going to observe the correct answer is like 0.9999. That's the one I want. So I was like, okay, what is this square root of n thing? All right, that's 16. Where does the 12 come from? Because it's obvious that I better not overshoot with my number of iterations. I better know exactly how many iterations to run if I want to get the right answer. I was confused by this. All right. So I said, okay, well, how can I need some insight into this problem. How do you figure out exactly how many iterations to run? Because it can't be just the square root of n. All right. It's approximately that, but it's not exactly that. And I needed to figure this out. So I said, all right, I extended my Excel spreadsheet and plotted these values, and this is what I get. I said, whoa, that looks like a sine wave and a cosine wave, doesn't it? I mean, that if you know, if that's not a sine wave, nothing is, right? And then I said to myself, okay, it's got to be a sine wave. This is not approximately a sine wave, because if you are rotating a vector and these components are the projection of that vector onto a basis vector, that's a sine wave. All right, that's what it is. So then I quickly realized, oh, of course, this really is a sine wave. All right, the orange one, which is the y amplitude, is a sine wave. And I'm looking for that peak right there. And the blue one is a corresponding cosine wave. So I had to figure out what these things were in order to figure out where you get this silly 12 from, or in general, what's the formula? And I figured if I want to know what that formula is, I better understand what that sine wave is, and so I can figure out where the peak is. So I said, okay, let's pretend that the y components is some sine wave and the x components are some cosine wave, where I've got some frequency omega and some phase shift phi, because that's the general form of a unit amplitude sine wave has two parameters, a frequency and a phase. So let me try to solve for the frequency and the phase, and then I'll know my sine wave, and then I'll know how many iterations to do. All right, now I'm going to do this. The literature does this exposition two ways. It does it geometrically and algebraically. All right, the geometric exposition is in some ways simpler, but for me, it's more confusing because I don't have good intuition about rotating complex vectors in a high-dimensional complex vector space. All right, I mean, I can read the explanation, but I was not able to convince myself that I understood it because I couldn't quite get my mind around what is a 1,000-dimensional complex vector look like when it's rotating. All right, I mean, if you can imagine that, I can't. So I'm going to do this algebraically, which is a little bit more detailed, but it's just algebra, right? And if you get the algebra right, you just can't possibly go wrong, you know? So here's the way this works. I said, okay, starting with the cosine wave for x, if I simply plug in k plus 1, all right, I can figure out what the x amplitude in the next iteration is. I just plug in k plus 1. I use a trigonometric identity to reduce this or expand this to this formula here, all right, which I can simplify kind of like that. Again, it's just a trigonometric identity and some algebra. And then I said, okay, remember that recurrence relationship we looked at a couple of minutes ago? I'll rearrange that like this. And now I have something where in order for these things to be equal, because they are both expressions for x sub k plus 1, it must be the case that this equals this, and it must be the case that this equals this. That's the only way that they are going to be equal all the time. And from that, I can get some formulas for the frequency of my sine and cosine wave as a function of the number of states. Now, I did this with x sub k plus 1. All right. By the way, you can work these out for yourself if you want to when I post the slides from today, but you don't have to. And I said, okay, well, I did that with the x components. What happens if I do it with the y components instead? All right. Do the same thing with y. Use my trigonometric identity like that, and then do the same thing with these recurrence relations and make the same equalities. All right. And I get the exact same formulas, which is a good thing, right? I mean, that's how I kind of knew that I probably had this correct, that you get the exact same formula for the frequency omega, whether you start with x or with y. So I was happy about that, real happy about that. So again, we're trying to figure out how many iterations we have. So those are my formulas. I'm going to start off with, this is a simple trigonometric identity for the half angle formula. That's just the half angle formula, nothing else. All right. Then I replace the cosine term with my formula here, right? Here. And this simplifies to, nicely, 1 over the square root of n. Nice and simple. Okay. And therefore, I can solve for frequency in this form. So I now have a formula for the frequency of my sine wave as a function of the number of states n. We're beginning to see that square root of n show up. We're going to see a little bit more about that in just a second. Okay, let's do this. Let's now figure out what that phase term is. Let's figure out what the phase term is, right? So the way to figure out the phase is to note that at iteration 0, we started off with an equal superposition of all the states. So x0 has to equal y0, because that's where we started. And if I plug that into these formulas, all right, I get basically something pretty simple, okay? Again, using some trigonometric identities, squaring some things, and I can solve for my phase. And it turns out that this phase is exactly equal to half the frequency. So I now know what my sine waves are. So what I'm going to do here is, there's my formula for the y amplitude. I now plug in what I know to be the frequency and the phase. All right. Factor out the frequency. And what I really want then is, in order to find the peak, since this is a sine function, I want this to be approximately pi over 2. Because pi over 2, that's where the sine wave is a maximum, very nearly 1.0. So what I'm hoping for, I want to find the value of k, because that's the number of iterations I'm looking for, that makes omega, this whole thing, approximately equal to pi over 2. And so I now plug in my formula for omega here, do a little bit of algebra. And to make this approximately equal, I am going to solve for k and round it off, because k is an integer. It's an integer number of iterations. And by the way you round something off is you add a half and take the floor. So if I add a half, this half term goes away, and I end up with, that's my formula for the number of iterations. It's a pretty hairy formula, but if you know how sine behaves for small angles, the small angle approximation to sine is just sine x equals x, or arcsine x equals x for small angles. So for any reasonable size of n, this approximates to pi over 4 times the square root of n. That's the number of iterations. And now you can see why this is order square root of n. Because the number of iterations to get the probability of measuring the correct answer to be almost exactly 1.0 is approximately pi over 4 times the square root of n, amazingly. All right. And if you, so what you can see is that pi over 4 is about, what, 3/4, something like that, 77% or whatever. So it's sort of 77% of this, a little bit less than the square root of n. That's it. That's how many iterations I need.
And that's where the 12 comes from.
Yes, that's where the 12 comes from. Exactly. That's where the 12 comes from. So we've done a lot of algebra, but again, the math is the math, right? These are the rules, and this is what it comes out to be. I've done some Google searches for this formula, and what you find is about this, but sometimes people are a little bit unclear about whether this half belongs in there or the use of the floor function. But this is in fact the correct formula for the number of iterations to get as close as possible to the correct answer, right? So that's Grover. Now, that's the theory. In order to turn this into an actual quantum algorithm, I'm going to have to show you gates that implement all of this, right? I'm going to have to actually show you how to build the machine. But this is the math. This is tells me that it works. Excuse me, that it's that these are unitary operations and exactly how many iterations I need. All right. Questions with this craziness? All right. So again, this is amplitude amplification used not just in Grover, but in a lot of algorithms. And this quantum oracle of marking a winning state with phase kickback, again, it's used all over the place in quantum computing. All right. So we got to make a circuit that can do amplitude amplification. And this is a little, I'm thinking, here's what I'm thinking. All right. What I'm thinking is we got 10 minutes to go. I'm thinking we're going to stop here because this is kind of the beginning of a whole new train of thought as to how to turn amplitude amplification into a circuit that uses the gates that we're familiar with, the Hadamard Gate, the NOT gate, and the Toffoli Gate, all right, to make amplitude amplification. And so being the beginning of kind of a whole new train of thought, rather than getting partway into it and then trying to resume next time, I think what we'll do is stop here and see if folks have any final questions about this stuff. And if not, I will see you in 2 weeks and I will post the recording and the slides. So how's everybody doing? Comments?
Thanks, Bill. That was really interesting. And that was very clear. Demonstration of the square root of n. Very nice for that search basis.
Yeah. Of course, there's an assumption that the oracle itself can produce the answer in, a reasonable amount of time. I mean, either constant time or maybe log n time, which it usually can. Any other feedback? It's kind of, with Zoom, it's kind of hard to tell how people are feeling about it. I can't quite see everybody's body language. Is the pace okay?
We all feel this in our teaching.
Yeah. What do you all think?
I was sort of blown away by the idea of an algorithm that gets you close to the answer and then goes away from the answer again, that it's periodically approaches the answer. And I was trying to figure out why those amplitudes have become negative, the non-winner amplitudes. And I think I can sort of see as the winner grows in amplitude and the average gets close to zero, that when you flip across, at some point you actually flip across zero, you actually reflect across zero.
Yeah.
It's just hard. It's weird because I'm no algorithm expert, but I've never seen an algorithm that
Yeah, and what you have to keep in mind is what helped me to understand it is that the only thing we are doing is rotating a vector. And when you rotate a vector, its components are going to be sine waves, right? They can't be anything else but sine waves, because these are all linear operations. Everything we're doing here is linear algebra. And when you rotate a vector and look at its components, they're sine waves.
And I guess from that perspective, you can also see why it approaches a solution and then goes away from the solution, because it keeps rotating away and then comes back.
Correct. And when I first looked at this and I was confused, I also did not understand why it overshot and started going down again, because I hadn't quite made this connection. Oh, of course, I'm rotating a vector. I was so stuck in the algebra that I sort of forgot the geometry.
Right. Yeah. Well, that's cool. Oh, very good. I'll echo what Liz said. This is really fun. Really fun stuff.
Good. I've certainly enjoyed putting this together. Things are going to get building the circuit's going to be interesting. And then when we get into, I mean, like I said, I've actually programmed this in Python and run it on real quantum computers as well as simulators. And the results are interesting. We're going to see that probably the last session. All right, anything else? Well, I really appreciate everybody's attendance and feedback.
Thanks a lot, Bill. Appreciate
And
it.
we'll
Thank
see you in
you.
2 weeks.
Thanks, Bill.
Bye.
All right, you're welcome. Take care. Yeah.